Really thrilled to be able to introduce our keynotes today. We're going to have some really incredible presentations followed by a panel discussion. And as all of you are very much aware, emerging environmental and climate applications have been totally redefined thanks to innovations with how and when certain pieces of data can be captured. The past data has seen an explosion in the availability of remotely sensed data, and that data is creating countless opportunities when it comes to understanding the way in which environment and our entire world is changing right before our eyes. Our keynotes are going to explore what these redefinitions look like across the world and beyond, with each speaker detailing the opportunities that the capture of this data can open up for single individuals and entire organizations in the short and long term. First up is Tara O'Shea, Director of Forest Programs at Planet. In this role, she oversees the company's strategy for leveraging its Earth observation and analytics technologies to improve global forest monitoring systems today and account for the value of forests in the global economy tomorrow. Prior to joining Planet, Tara advised several foundations and investment firms on integrating the reality of climate and environmental change into their portfolios. Please join me in welcoming Tara O'Shea.
Good morning. Thank you, Jeremiah, and to the whole GeoWeek team for having us here. I'm really excited for this conversation. I fully agree. I think there's a whole new world happening in climate and environmental applications. In no small part thanks to the explosion of remotely sensed data that we have. So a quick overview of what I'm going to talk about today. I'm excited to share more about Planet's Earth observation constellations and data sets, talk a little bit about our solutions for forest monitoring, and then give some examples of how, folks are combining our data set with LiDAR data sets for new applications in forests and climate. So for those who are not familiar with Planet, I tend to say that we have a little bit of a mantra, and that's that you can't fix what you can't see. We think that this is ultimately at the root of many of our sustainability and climate challenges, and it's a small piece of the puzzle that we're trying to help solve with space and Earth observation technologies and data sets. So our mission is to image the full Earth every day in order to make global change visible, accessible, and actionable. Okay, so how do we do that? How do you go about imaging the full Earth every day? Well, we have actually created, launched, and now operate the largest constellation of Earth-observing satellites in human history, but most of these satellites are in fact quite small. So what you're seeing here is an illustration of our Dove constellation. This is made up of over 100 small satellites in a sun-synchronous orbit, such that as the Earth rotates underneath them, they image the same place at the same time every day at about 3.5 meters per pixel. This is in 4 spectral bands going to 8 spectral bands. Now, this sort of broad area, always-on monitoring is also complemented by our SkySat constellation, which you now see illustrated here. These are very high-resolution tasked systems, so they can image anywhere daily at 50 centimeters per pixel, also in 4-band and video. So I like to show this illustration because I think it gives you a sense for the unprecedented Earth observation capacity that this is helping bring online, in terms of spatial and temporal resolutions especially. It's extremely complementary to several of the other data sets that we all know and are discussing further here today. So a lot of our users and customers actually end up using the two systems in tandem, as you see here, using that broad area daily monitoring to detect change, and then zooming in with the 50 centimeter tasked system. So what drives value for our customers? Again, if you're going to take anything away from my presentation today, it's this idea of high spatial and temporal resolutions over broad areas. It's the idea that you can have that precision at scale. And then remember what I said about our mission, that last piece was making global change accessible. We take that piece very seriously with our delivery. So we're very much an API-first, delivery-based company. We want to meet you where your operational workflows are today and make it a lot easier to bring geospatial information into those decision-making processes. Okay, so what does this mean for forests and climate? Well, I think that we're very fortunate in the forest monitoring world. We have had Earth observing satellites help us understand changes in forests and land use for decades, thanks to the Landsat mission. Obviously, there are many public missions and private missions, but I think we're actually in a better place when it comes to forests than some of the other climate challenges that we have, because we've had these tools for so long and had the investment of the scientific and public communities. What Planet is bringing online that complements many of these other data sets that we're talking about today, again, is that spatial and temporal glimpse. So what you see here is an example from Brazil. This is that 3.5 meter resolution that I mentioned. The white lines are actually property boundaries. So you can see with the high spatial resolution, you can zoom in and actually understand where is change occurring. You can combine that with other information sets and make that more actionable. I like to show this example. This is actually from our customer and partner at the Forestry Department of the Food and Agriculture Organization of the United Nations. And I think this shows really well how they're able to use Planet data in conjunction with other public data sets to zoom in on change, including, and we'll show a couple more examples, but including the kind of green over effect of regeneration and regrowth, right? These are all details that sometimes we miss at lower spatial and temporal resolutions. And when we combine everything together, we get much more information. This is an example from the Congo Basin. So this is the eastern DRC. I like to show this example for a couple of reasons. So one, I tend to say looking at forests and Planet data, it looks like broccoli, right? Like you can see the spatial structure of the canopies there. It's not a flat green pixel. And that's really important for some of the LiDAR collaborations and fusions that we're going to talk about in a minute here. So this is that same area just a few months later. So, there's obviously a lot of change happening in that small time frame that we maybe were missing with our annual measurement, reporting, and verification systems. You can see degradation happening, right? You can see the removal of individual large tree crowns. You can see roads, very small informal roads that are often a precursor to deforestation. And then again, just a couple of months later, you can see the areas that start to green back over. But again, because of the higher spatial resolution, you can tell that those are actually flatter pixels, right? That is newer vegetation. It's not the same as the old growth trees that were removed with that degradation. Similarly, I mentioned that SkySat constellation and that many people use the two in tandem. So this is what forests look like in that 50 centimeter resolution. This is actually an example from the Peruvian Amazon, but you can see again why folks might want to use these two in tandem. And also you can see that broccoli effect is really amplified here, right? Even with your eye, you can make out a lot more of the spatial texture of the canopies. So I just like to show this example kind of as that tip and cue workflow. This is from our partners at Amazon Conservation, who, as they noticed changes happening in the Planet Scope 3.5 meter data of new roads being emerged, they actually tipped a SkySat to that area, and you can see they could actually capture logging trucks in that image, which I thought was pretty amazing. I'd never seen an example like that before. So what does this mean for our forest monitoring systems, for the reporting systems that we have set up under the Paris Agreement and others? We're seeing a lot of adoption of this high-res data into improving forest area change estimations. So I'm just going to show a couple examples of that here. This is an example from the government of Mozambique. We have a contract and partnership with the Norwegian Ministry of Climate and Environment, which provides this high-resolution monitoring into many of the tropical government's programs, including further measurement and verification within the Paris Agreement commitments. So what you see on the left is the annual lower resolution change measurement in forest area. The red indicates deforestation over the course of a year. On the right is how the government of Mozambique is now incorporating this higher spatial and temporal resolution data to automatically validate and measure that change at higher frequencies. The example you see, this is actually using the Planet data within Google Earth Engine, which is another, I think, just really cool parallel innovation happening alongside remote sensing as some of these cloud-based geospatial platforms. Similarly, this is again an example from the Congo Basin. The 6 Congo Basin countries are now using this high resolution data not only to improve the detection and measurement of degradation, which we looked at earlier, but also to better understand drivers of deforestation. So we can see actually what is this land that's being converted to, and how can we better manage that with improved policies and interventions. So that's kind of forest monitoring systems as they exist today, I would say, and how they're adopting some of these new technologies and remotely sensed data sets that we're talking about. But another area that's really exciting and I think really relevant to the folks in this room and the innovations that everyone's doing, which is combining different data sets. So we're actually seeing a lot of our downstream customers, partners, academics, starting to combine planet data with aerial LiDAR data to improve our understanding of forest inventory, biomass, and carbon. So I'll just show a couple examples of that now. I think many folks in this room are very familiar with LiDAR data. We're going to hear from some experts on LiDAR data. But I will just say, there's been so many advances in recent years with using LiDAR to measure forest biomass and carbon. And what you see here, you get this nice 3D picture back of the forest, and it's really helpful in a conservation practitioner sense to understand this is where we have the highest carbon stocks, and that should help inform perhaps some of the planning and conservation. So as those advances are being made, we have also started to see many of our downstream academic users and now increasingly commercial users start to think about, what if you could correlate this aerial LiDAR image, which in the tropics, we might only have in certain space and time instances because the tropics are huge and it's expensive to get aerial LiDAR at the resolution that you see here. And so we've seen more users start to say, well, what if you could combine Planet's high resolution optical data coming down from space every day with LiDAR to train a model? Could you extract those volumetric measures across space and time? And so that's exactly what, again, we've started to see more of our users do. And I just think this is a really fascinating area with big implications for how we might actually, in practice, be able to measure and manage some of these things. So this is one example from Arizona State University. This is Dr. Greg Asner's group at the Center for Global Discovery and Conservation Science. They were actually able to use this approach across the whole country of Peru, where they had collected several samples of aerial LiDAR data. So what you see here is kind of the outputs of the model once it's trained on the aerial LiDAR and then powered with Planet's broad area mosaics. So you can see that they're able to map the carbon stocks and then kind of subtract over 2 time periods and look at emissions of certain activities. His team has published probably like 3 or 4 papers at this point on some of these approaches. If anyone's interested, you can find those linked, I think, both at Planet and at their center's website. But the exciting thing is the outputs of the model really do have a very strong correlation with the LiDAR-based samples and measurements that his team had done with some of their initial carbon mapping in the country. Similarly, I mentioned we're seeing this, not just in forest carbon, but also in biomass mapping. So this is extremely relevant for things like wildfire risk mapping. What you see here is a Planet image of the Sierra Nevada foothills in California, where I live and where obviously we have a lot of challenges with wildfires in recent years. Again, you can kind of see the detail that is available at this resolution, especially in terms of that broccoli effect on the vegetation, right? So this was previous biomass mapping of that region. And this is from one of our commercial partners, Salo Sciences. They created this map for an effort called the California Forest Observatory. And you can see this is the output when they used the same approach, essentially. Trained a model using airborne LiDAR over the area, and then kind of scaled the tree height information using PlanetScope. And what's interesting about this, if you can go to, just Google the California Forest Observatory, you can play with some of these maps. This was supported by the Gordon and Betty Moore Foundation in California. What's really interesting, they took this biomass layer, and then once they combined that with things like wind and weather, they could actually create a more comprehensive high spatial and temporal resolution map of wildfire risk. So this is really, the idea is, rather than just responding to wildfire, which is a really critical use case, how do we also think about risk reduction and the way that these remotely sensed data sets and technologies can help us do that as well. So with that, I think that's it, and I think we'll have time for Q&A after, so I'll go ahead and hand it back to Jeremiah and the next speaker.